Could you please make very, very welcome for her second and final lecture, Professor Kylie Catchpole.
So thank you very much, Chris. Yes, today I'm going to be talking about solar energy, which is my own area of research, so we can go into a lot more detail. Firstly, one of the main points from yesterday was the vast solar resource that we have. So this is showing you a bit more visually. What we have here is a map of the solar radiation in Australia, and we have this red dot here, which is the area of Australia that we would need if we wanted to provide all Australia's electricity from solar. And if we were slightly more ambitious and wanted to supply the entire world's electricity, that is the area of Australia that we would need. So you can see, obviously, we do not want to cover a large fraction of the Northern Territory with solar panels, but you can see that we have a vast amount, plenty for Australia and plenty more to export to the world if we wanted to do that. So I mentioned yesterday there's a range of different types of solar energy. So we have solar photovoltaics, which is directly converting sunlight to electricity. We have solar hot water, which is just using the energy from the sun very simply to heat up water. We have passive solar, which is light coming in through your windows to warm up your house. And we have solar thermal, where you're concentrating the light from the sun to create heat, to then create steam and then turn a turbine. So those are the range of different types of solar energy. We're going to focus today on solar photovoltaics, which is my area of research. Just to introduce our research group at the ANU, we've got about 60 staff and students, PhD students, working in this general area in renewable and sustainable energy, particularly high-efficiency silicon solar cells, new materials for solar cells, which is my area of research, grid integration and battery storage and integration, as well as solar thermal. And you can see we do get some high-profile visitors. This is the former Prime Minister Julia Gillard visiting our laser lab and being illuminated by a rather strong laser. We use these lasers for actually cutting through pieces of silicon, so they're very powerful types of lasers. So I mentioned yesterday that we've seen a dramatic reduction in the cost of solar energy. So you can see here the price dropping down dramatically by orders of magnitude, but we can understand this in a more quantitative way if we look at it a little bit differently. So just by looking at that, it's not totally obvious what's going to happen next. But we can look at it more quantitatively and we can make some predictions then about the future. So what I'm plotting here is the same thing as on the previous graph. This time it's being plotted on a log-log scale. So you can see what we've got here is a logarithmic scale on the y-axis and also a logarithmic scale on the x-axis. So what we're plotting there is the price versus the cumulative production. That means the amount of photovoltaic solar panels that have ever been shipped. Okay, and we can see that there's actually a linear relationship if we plot it on a log-log scale. So it was an exponential type decay, but now if we plot it on a log-log scale, it becomes linear, and that means you can extrapolate out and you can predict what's going to happen in the future. This is a very important concept because what we find is that the price decreases by about 20% every time you double the cumulative production. We can also see that so far it's keeping going. A few little bumps in the road, but so far the overall trend is continuing, and that means we can expect the price to continue to decline. This is a characteristic of every single technology. When you make new technologies, what happens is that the price decreases as you continue to produce more of whatever it is. It's due to economies of scale, it's due to technology development. So we can see that for photovoltaics, this is continuing, and that means the price is going to continue to fall. At a certain point for any technology, this stops, and you end up with the prices pretty much the same. And this is where things are at. For example, for coal power, the price is not going to get lower by making more. In fact, for the fossil fuel type power stations, the price tends to increase because the emission standards tend to get higher, and we don't want to emit so much pollution, so it actually gets a bit more expensive to build them. But for photovoltaics, the price is keeping decreasing, so we can expect that to continue in the future. We can also look at what's happening then on a country-by-country basis. So this is again the price, and this is versus time now. So the yellow dots are solar prices in various countries, and the blue dots are wind. So you can see 5 or so years ago, solar was significantly more expensive than wind, but the price has come down to a point where they're pretty similar now. It does depend on the country. Some countries are more expensive than others due to labour prices, for example. Some countries are cheaper than others due to the amount of resource, whether it's wind resource or solar resource. But overall, the prices of both are coming down, and solar and wind are now pretty similar in price. We can see the dramatic increase in the amount of installations that's happened in Australia. In Australia, it really took off around 2008, so we had around 20,000 systems installed across all of Australia in 2008, and it's been increasing rapidly ever since, and now we're up to about 1.7 million. So this is quite a significant fraction, 20 or 30% or so of all the residential houses in Australia. So it's quite a significant amount, and it's because of that dramatic reduction in price that we've seen. So we can think, okay, given that the price has fallen, given that the amount is increasing that we're installing, where can this take us? How far can we go if we keep going on this sort of path? So this shows you somewhere where we are at the moment. We're plotting here the installed or produced capacity in terawatts, remembering what terawatts are, 15 or so terawatts being the entire world's electricity supply at the moment. And you can see here, this is the annual market deployment in gigawatts. So this is the amount that you're installing each year in the blue, and in the yellow, how much you've installed overall. So you can predict this into the future. Here we are, somewhere around here. If we keep going at the same rate, if we keep increasing each year at the same rate that we've been increasing, and then sometime around 2030 or so, we level off and we keep just installing the same amount each year. If we do that, we can predict into the future, and we can say that by 2050 or so, we could be producing around 44% of the world's electricity using solar. So this means we're actually already installing, we're on the path that we need to be following if we want to install a very large fraction of the world's energy from solar by around 2050. I mentioned yesterday the different types of installations that we have. So here's the small type systems or moderate type systems on people's houses. Depends how much roof space you have, of course, and which direction your roof is facing. You can have moderate scale systems. Here are commercial systems on buildings. This is a market that's not really been developed all that much, but it's generally very attractive for businesses to put solar panels on their roofs because the electricity is being produced in the daytime, and which is the same time that businesses are using it. So this was one of the early ones in Alice Springs, which is right in the middle of Australia. And it was particularly attractive to install this one because in Alice Springs, they don't have an electricity grid that's connected to the rest of Australia. They have their own isolated electricity grid, and because of that, their electricity is more expensive than in the rest of Australia. Here's the first solar farm in Australia. So that was in Western Australia. That's a 10 megawatt system, and you can just kind of see the panels so you can get an idea of the size of this sort of system. Now, as I mentioned yesterday, they're making much bigger solar farms. So this is a 100 megawatt solar farm. So this is a much more substantial system, and then it's so large you can't actually see the individual panels of the system. But the unique thing about solar photovoltaics is that you can install on these range of scales without making very much difference in price. You can install it on your house, you can install a moderate-sized system near a city, or you can install a very large system in a rural area, and all of these can be cost-effective. So we can see then, in order to produce all these panels, solar photovoltaics has to be a big business. We have to be producing these sort of panels at a pretty high rate. This is an individual cell of the panel, so the panel is made up of tens of these individual cells, and in a factory you're usually making those cells at about 1 cell per second. So this is pretty challenging for those of us in research, because anything that we want to do to improve that cell has to be compatible with making those cells at 1 cell per second. So it's very challenging. And then the factories themselves will be producing maybe a gigawatt of power over a year. You'd have typically a number of production lines. The whole factory would be about half a kilometre long. So very big business, putting out around 600,000 modules per year. So let's now go back to the beginning and learn a little bit about how this all happened and how these solar cells actually worked. So the story starts with Edmund Becquerel in 1839. He was 19 years old. He was working in his father's lab, and he had a kind of electrolyte solution with some silver in it, with some platinum, and he discovered it was essentially a electrolytic sort of battery type system producing a voltage and a current. But what he discovered was that when he put light on the system, he would actually get more current out. So it was sensitive to light, and it was producing a voltage and a current. So this is the beginning of the idea of a photovoltaic effect. The systems we have now, of course, are completely different, but that was the beginning. What happened after that? Well, in 1876, the first photovoltaic effect with selenium was discovered. This is much more close to what we have now because it was in a solid state material, and they discovered you could actually get a voltage and a current out of selenium when it's exposed to light. And even in 1883, so not very much longer after that, Fritz actually designed a photovoltaic cell. He had the idea, okay, we can use this to make electricity using selenium. But he was kind of well before his time, really, because they didn't understand at all what was going on in these materials, so they had really no way to engineer them. We then have around 1900 or so the whole quantum theory of light, which is necessary in order to understand how photovoltaic systems can work, because they depend on the fact that there's a certain energy associated with each wavelength of light. And if you don't have that idea, you can't really understand how the system works. And it also depended on materials development. So this was making a single crystal of silicon, and if you don't have high quality materials, you also can't get working solar cells. So you can see we have a mixture of things. We have people just trying things and seeing what's happened, and then you don't really understand it. You've got some effect, you don't really know what's going on. You have theorists who are working out the fundamental theoretical understanding of how to understand this concept. You have materials people actually making nice quality materials, not necessarily with any particular aim in mind, but working on techniques. And finally, if you put all those things together, then you can actually get something that works well. So this then led up to 1954, the first photovoltaic cells being made at Bell Labs, and very shortly after that, solar cells being commercially available. So these were pretty inefficient at that point, only 6% or so, but it was enough so that people could actually see the promise of this technology now. They could see how it could move forward. They could understand what was going on. And of course, this was a time also where silicon was being rapidly developed for transistor applications for computers. So there's a lot of technology development all happening at the same time. So what's happened since then? Well, this shows you the record efficiency chart of solar cells. And you can see that we're starting here in 1975, so 25 or so years after that invention of those first low-efficiency silicon cells. And we have a range of developments. So we're just focusing on silicon for the moment, so that's the blue. So you can see by that point the efficiency had increased by 12% or so. And since then, it's been increasing gradually in efficiency and then more or less stabilized in efficiency. But silicon is the basis for almost all the solar cells on the market at the moment, so that's very important. We also have a range of thin film technologies, so there are various types of materials. The most well-known is cadmium telluride, which is also commercially available at the moment and at a similar sort of price to silicon, but a small fraction of the market compared to silicon. We have some very high efficiency solar cells up here, and those are the sorts of solar cells that you will see on satellites. Firstly, on the race cars that go across the desert where you want the very highest efficiency and you don't care so much about the cost. So those types of solar cells can be much more efficient, more than 40% or so, but in that case they're much more expensive than silicon solar cells, so we don't put them on our roofs. And at the bottom we have a range of different new materials that have been just emerging over the last few years, very different materials and concepts, and I'll talk to you some more about them later. But let's now look at how solar cells actually work. So the fundamental concept is that we have sunlight coming in, hitting your solar panel. Now we have a look at the cross-section of your solar panel, and what we have for a silicon solar cell, we have some N-type silicon and some P-type silicon, and the junction between those two materials. And what happens is that when the sunlight hits the solar panel, you only allow electrons to flow in one direction. That means the electrons will flow in one direction, and so you create a current. So a solar cell is essentially a current source. You can then put some kind of load across there, and you develop a voltage drop because you have a load there. So we've got then a current and a voltage, and so we can get energy out of the system. Looking at it a slightly different way, what we have here is the sun coming in. We create excited electrons. We leave behind then what we call holes, which is a space where an electron used to be. Now the electrons can go in one direction, but the holes can actually travel in another direction. Now I have to say I didn't believe in the concept of holes for quite some years. So you don't necessarily have to straight away, but what it is a gap where an electron used to be, and that gap can move because the electron is hopping the other way. So essentially it's the space where the electron used to be traveling in the other direction. Whoops, let's come back here. Then what you want to do if you want to design the solar cell is you obviously want to promote photogeneration, so you want electrons to be excited by the sunlight coming in. You want to suppress recombination. That means you don't want the electrons to recombine with the holes because then you get nothing. You want to allow the electrons to go in one direction, and you want the holes to go in another direction. So this is what you need to do in order to design an efficient solar cell. So looking at the solar cell now in terms of physically what it is and in terms of what the voltage and current you get out of the solar cell. Here's that solar cell. Again, we have the light coming in. It's absorbed in this sort of blue-black section. That's the silicon. And then the electrons will come out along to the metal contact and go through the external circuit. Now, a solar cell is actually just a diode. It's the same thing. Conceptually, electronically, it's the same thing as a diode that you might see in an electronics kit, in any kind of electronic thing that you pull apart. A diode just lets current flow in one direction, and the solar cell does the same thing, but the solar cell lets the light in. It's designed, it's basically like a diode that you've spread out in order to let the light into, and then we have the same thing. So we then also have an anode and a cathode, and we have, well, conventional current flowing that way through the diode. So we can understand electronically then how a solar cell works if you think of it like a diode. So this is the current voltage curve for a diode. So we have the voltage on the x-axis here and the current on the y-axis. Now a diode lets current flow in one direction. So if you take it into reverse bias, it lets basically very little current flow at all. But if you take it into forward bias, then it lets a large amount of current through. So we have an exponential kind of relationship. That's the current voltage relationship for a diode. So we can write this down in terms of an equation. So here we have this exponential function here. I've written exp, that just means e to the power of, so for those people who haven't seen that. And so if you take it into reverse bias, you have a negative voltage here. So this thing is very, very small. And so you can forget about it. And then we just have minus I naught. I naught is very, very small, so you have this tiny, tiny voltage, tiny, tiny current here. Conversely, if we apply a forward bias, so we have a positive voltage here, then this exponential gets very, very large. So we can forget about this minus 1. Essentially, we have an exponential, and of course, it just goes up very fast. So that's the current voltage relationship for a diode. So physically, what does this correspond to? Well, this is the energy band diagram for a diode. So what we're showing here now is the p-type region of silicon and the n-type region of silicon. So the silicon material has the same electronic band gap. This is the space between here and here, and here and here. But the p-type and n-type just shifts those. And what we here have an electron sitting in the conduction band of the material, and it can't go this way because there's an energy barrier to stop it going that way. So it can only go the other way. So this is physically how a diode is working. Essentially, these are the electronic levels that the electrons can travel in, and there's an energy barrier that stops them from going in one direction. So if we have a solar cell, we have the same thing, only now we're letting light in. So we have the same band diagram as we had before, but this time the light is coming in, it's exciting an electron up to here, and the electron can fall down the barrier, and it can get out as a current. So it's essentially the same thing as a diode, but when you let the light in, then you're letting some current flow in the region where current couldn't flow previously. So we can see this then in the relationship between current and voltage for a solar cell. So in this region, where previously we had almost no current flow, we now have quite a big current flow. We've got this light-generated current, which is coming across in this term here. And apart from that, the whole thing is the same as the diode curve. So essentially, we have the diode-type behavior, but we also have this extra light-generated current. And this means we have this little region here where we've got voltage and current coming out of the system, and that means we can get energy out. We've got voltage and current, so we can get energy. So this is the bit that we're interested in designing a solar cell. Okay, so how much power can you get out of a solar cell? It's always good to get a feel for the size of these kinds of numbers. So for this kind of solar cell, this is about 12 centimetres or so across. You'd have an efficiency of maybe 15% for one you just bought. We've got the solar irradiation coming in, which is about 0.1 watts per centimetre squared. So that's how much intensity that you get from the sun on a bright sunny day. And so you can work out how much power you would get out of one of these. You can multiply the efficiency by the area, by the amount of irradiance from the sun coming in, and you can work out that you'll get a couple of watts out of just one solar cell. And then the whole panel is made up of tens of solar cells, so you can get a feel for the amount of power that you get out of one panel. So these are sorts of commercially available panels. The very highest efficient ones are around 22 to 24%. They're very high efficiency. They're somewhat more expensive than the other types of panels. Here's your more typical types of panels, around 16 or 18%. So these are the sorts of panels that you would buy to put on your house. Okay, so let's zoom in a little bit and find out how they make these silicon solar cells now. So we've found out how they actually work, and how do you actually get that panel? What's the process of getting there? So we'll have a look, and we can see the cross-section of the solar cells. So here we have the N and P type bit that we were talking about before. That's the crucial way that the actual solar cell works. And when we have a few other layers in the solar cell, anti-reflection to make it not reflect too much light, so that's why you have this kind of blue color on the solar cell. The metal contacts are, of course, on each type of the solar cell. Okay, so what we do is we start with quartz. So just rocks, basically, dig them out of the ground. You need to get to silicon, so this is quartzite, so this is essentially silicon dioxide. Plus a few other things in it, and you need to get to silicon. So what you do is you put it in a furnace together with some low ash coal, and you apply a great big current to it. So this is an electric arc furnace, and what happens here is that the coal reacts with the oxygen and leaves you with just some silicon. So then you have these great blocks of what's called metallurgical grade silicon, so it's essentially kind of silicon rocks. They've got 1 or 2% of impurities in it. So it's good, it's silicon, that's what we wanted, but it's not pure enough yet. It won't work electronically well when it's got these kind of impurities in it. So we've got to do something about that. So what we do is actually distill it. So you wouldn't believe that you could actually distill these kind of rock-type materials, but you can. So what you have to do is take your metallurgical grade silicon and dissolve it with a chlorination process. So you end up with a liquid called chlorosilane, and then you distill that lots and lots of times. Distillation processes, you know, and can get rid of any kinds of impurities in a material. So as a result of going through this process, we can end up with semiconductor grade silicon, which is 99.99999% pure. So then that's something that you can use to make solar cells and also to make computer chips. So they need ultra pure silicon for the same reason in order to make computer chips. Then once you've got your ultra pure silicon, you need to make it into a wafer type structure. So you need to first make it into some kind of block. So this is casting multicrystalline silicon. In this case, you want to have large crystals in the material. So you know that if you want large crystals, you have to do things slowly. So cooling things slowly so the crystals can slowly grow. So here they actually put the silicon into a crucible and then slowly heat it and slowly cool it, and then you can end up with these great big blocks of silicon with some large crystals in it. If you want even better quality, you can actually make single crystals of silicon. So what we're doing now, this is a bit like growing salt crystals in a kind of beaker. You start with some kind of seed crystal. You have the molten silicon in this case, and then you very, very slowly pull the seed crystal out, and the silicon grows on the seed crystal. And so these great big rods are in fact one crystal of silicon. So once you've done that, you can slice it up into wafers using a saw. Then this is a crucial bit. You need to make the PN junction. So we now have just a wafer of silicon. It'll be probably P-type, which means it's got a little bit of boron in it. And in order to make that junction, you want to have a thin layer of N-type, which is a thin layer with some phosphorus on the surface. So what you do is you put it in a furnace and have some gas with some phosphorus in it, and that'll make a thin layer on the surface which has got a bit of phosphorus in it, and that creates your PN junction. So the phosphorus is, the reason why that works is that it's a group 5 element, so it has an extra electron compared to silicon, which is a group 4 element, and so that changes the electronic structure of the material, so you have extra electrons compared to the p-type bit, which has boron, which has fewer electrons, and so that changes the electronic band structure of the material. And so then we create this junction. So this is what it looks like in our labs with the furnace going in and the wafers going into the furnace, and this is what it looks like in a factory. And you can see these guys are all dressed up because we don't want any impurities to get into the solar cell, because we just put a lot of effort into making sure that everything was really clean, and we don't want any impurities to get into the solar cells. So finally, then you can finish your solar cell. We've got the N-type and P-type bit here, and we can finish the solar cell by depositing an anti-reflection coating and depositing the contacts, and then you've got your solar cell. And then it's just a matter of assembling those solar cells into a module with some glass and with some frame. Okay, so I mentioned before the efficiency chart, and I said that silicon has kind of flattened out. So we have this kind of, here we go, it's kind of flattened out over since the 1990s. The efficiency of silicon solar cells is not increasing. And there's a fundamental reason for that, and it's because of the electronic band structure of the material. So again, this is this solar cell band diagram that we saw before. I've just added in a few extra things in here to show you how you lose energy in a solar cell and why the efficiency is fundamentally limited. So what we have here is light coming in. We've got different colours of light coming in. Now with the red light, you would just excite from near the band edge right to the top near the band edge. So solar cells can use red light very efficiently, right? Because you don't have extra energy. But if you have blue light, this is what's happening with the blue light. We excite the hole from down here and the electron from way up here. So we have this extra energy. The blue light has extra energy compared to the red light, and we can't use that extra energy in a standard silicon solar cell. What happens is the electron just falls down pretty quickly down to here, and that extra energy is just lost as heat. So that's one issue, and the other issue, if you have light that is lower energy than that red light, then you can't absorb it at all. So that if the energy of the light is smaller than this gap here, then you just won't absorb it at all, and it will just go straight through. Okay, so those two things fundamentally limit the efficiency of solar cells to around 30%. Okay, so that's quite a big loss, and it's just because of the solar spectrum, just because blue light has a lot more energy than red light. We have a number of other losses in here, but I won't talk about them right now. So what can we do about that? One solution is to use what's called a tandem solar cell. So what we're doing here is we're stacking a few different solar cells on top of each other. Okay, so these solar cells can have different electronic band gaps, and that means you can make much better use of the solar spectrum. So this one on top has a high band gap, so it's good at absorbing the blue light. The one in the middle would have a moderate band gap, and it would be good at absorbing maybe the yellow light, and the one at the bottom would have a low band gap and it would be good at absorbing the red light. So you put these types of solar cells together, and then you can get a very high efficiency overall. And this is why the solar cells that I talked about that they put on satellites can have such high efficiencies, over 40% or so, is because they're stacking different materials on top of each other. Then you can use it to get a higher efficiency overall. But with those materials, they're really expensive, so you can't use them on standard rooftops. So this is what we're doing in my lab at the moment. We're looking at new ways to stack different solar cells in what's called a tandem configuration so that we can increase the efficiency overall. So we're starting out with a silicon solar cell on the bottom because we know silicon solar cells are already in production, they're cheap, they're efficient, so they're good. And we're thinking, okay, what can we put on top so that we can increase the efficiency overall? And if we can do that, you can see then the light is absorbed in the top cell and the rest of the light is absorbed in the bottom cell. So when we started this work, we looked at a whole range of materials and tried to figure out, well, what's the best choice of material to actually put on top for this tandem type structure. And you can see here are some of the materials that we thought about, but all these types of materials, the band gap is okay, they're absorbing blue light, which is good, but the efficiency of the solar cells was still really low. And so if you put a low efficiency solar cell on top of a silicon solar cell, all you're going to do is make the whole system worse. So it's important to start with something that's pretty high efficiency. Now, when we started this, there was a new type of material just being developed called Perovskite. And that material has increased in efficiency really fast, so now the highest efficiencies are 22%. So this is a really promising material for putting on top of silicon solar cells. But what you need to do is you need to make it high efficiency, and you also need to make it transparent to the red light so that the red light can pass through the top cell and go and hit the silicon solar cell. So this, I said I'd get back to it, this is the perovskite efficiencies just over the last few years. So you can see that they've been rocketing up in efficiency much faster than any other material. So they've increased their efficiency super, super fast. In 2009 was the first report of a solar cell with this efficiency, and it had an efficiency of around 3%. So in 2009, it was just one of a whole heap of materials that made really bad solar cells. But it was developed really quickly, and finally we've got an efficiency now of around 22% with these materials, and they're still developing. So very promising for making new types of solar cells. So what is a perovskite actually? Well, perovskite actually refers to the crystal structure of the material. So this shows you the crystal structure of a perovskite material. And now the particular ones that we're using are called hybrid organic, inorganic perovskites. They're a bit of a mixture. So this one is methyl ammonium lead iodide. So it's combining the methyl groups, the ammonium groups, the lead and the iodide. So there's various different elements that are used in the perovskite, but they all have the same perovskite crystal structure. And this shows you the band gaps of the material. So this is the active material. This is where we excite the electron, and then the electrons can travel over to the contact, and the holes will travel the other way. Now, what we've got over here is a couple of electron micrographs of the materials, and you can see this is completely different from a silicon solar cell. It looks really, really different. So this one is a top view. So we're looking with an electron microscope at the material, and we're seeing lots and lots of little grains. So those grains are only about 200 nanometers in size. So we said for silicon, the crystal can actually be the size of the entire cell, so like 12 centimeters or so. These ones are only 200 nanometers or so. Now we're looking up here at the cross-section of the material, so we actually cut through the cell and we look at the cross-section, and this whole thickness is only around a micron or so. So very thin materials made of very small grains, so it's operating quite differently, but we can still make high-efficiency solar cells out of it. And what we have is the perovskite itself. We have some titanium dioxide. We have some layers to help transfer the electrons over here. And over here we have some layers to help transfer the holes out. So that shows you the structure of the solar cells we're making. When we're thinking about these types of solar cells, we have to figure out, okay, how are we going to engineer this solar cell? I said we needed to make sure that the solar cell was actually really transparent to red light. So this is the first thing that we thought about. How do we make sure that this solar cell is actually not going to make the silicon solar cell worse? So these perovskite solar cells have layers on top to help get the electrons and holes out. If we go back to the previous slide. So this is the indium tin oxide over here. So these are what's called transparent conducting oxides. So they kind of act like metals, but they're transparent, so they let the electrons out. We have to make sure that these layers don't absorb too much light, because typically these layers will absorb 10% or so of your light, and if you have two of them, then you're losing 20% or so straight away. So we have to make sure that we don't lose too much in these layers. So what we did was we engineered these transparent type layers to reduce the losses in those sorts of layers compared to the materials that you can buy. And this, what we did was we altered the thickness and exactly which layers we're using in the type of solar cell to make it as efficient as possible. And this shows you the result of doing this. So what we're plotting here is the absorption in the materials as a function of the wavelength of light. And the black line shows you what the standard materials are like. And by trying different combinations, we were able to get the absorption in those materials to only a few percent. So this is one step in the process to getting an efficient solar cell. So you have to think about all the different steps in the process and how you can reduce the losses everywhere in the process. So this is the result of doing that kind of engineering. We were able to make this solar cell so it had a transparency of more than 80% in the long wavelength region. So we're letting more than 80% of that long wavelength red light go through to the silicon solar cell, which we need that in order for the silicon solar cell to be efficient. The next thing we did was to look at the perovskite material itself so that we could increase the efficiency of the whole solar cell. So this shows you, again, the top view and the cross-sectional view of the different types of solar cells that we made. And you can see here's the control one, and there's kind of lots of grains everywhere, and it's a bit messy there. But by putting rubidium in, we made much nicer looking grains, and that makes it easier for the electrons to travel, and that means that the efficiency can be higher overall. So this shows you the result of the efficiencies. Without the rubidium, we had an efficiency of only 13% or so, but by putting the rubidium in, we could get up to an efficiency of 16% or so. And this shows you the current voltage curve. So remember the current voltage curve for a solar cell. This is what we want. We want current, high current and high voltage at the same time, and this we can get power out of the solar cell. And this was a measure of the light intensity when we shine light into the solar cell. We can see how long the electrons and holes last before they recombine. So with the rubidium, they were lasting longer, so that means the electronic quality is better and we can get a higher efficiency solar cell. So this is then the end result of all this engineering process. So what we've done is we've got the silicon solar cell, we've got the perovskite solar cell on top, and we can see this is how much of the current you get into the perovskite solar cell and how much you get into the silicon solar cell. So you can see across the whole solar spectrum, we're getting good current produced from both the perovskite solar cell and from the silicon solar cell. If we put it together, we were able to get an efficiency of 26% for the whole system. So this was the highest efficiency that's been achieved by putting a perovskite on a silicon solar cell like this. And the perovskites are important because this has been the first time that it's been possible to increase the efficiency of silicon solar cells using a low-cost process. So all the other ways that people have tried so far have been very expensive and way too expensive to do something that you could put on your rooftop. So this is an important way of increasing the efficiency of solar cells using a low-cost process. So perovskite solar cells do have some challenges, and one of the main challenges is the stability of the material. So I showed you the processing for the silicon solar cells, and it was a long and energy-intensive kind of process. You had to take it up to 1500 degrees at some point. But the result of all that is that the silicon solar cell is very stable. It's essentially like a rock, and unless you take it up to several hundred degrees, nothing is going to happen to it. The perovskite solar cells, on the other hand, are much more sensitive to heat and to moisture. They're very easy to process. You can actually just print them onto a material, but they are less stable than silicon. So one of the things that we need to do is to increase the stability. So what we found using the rubidium is that we could have higher stability than previously with the other composition of materials inside the perovskite. So putting the rubidium in helped the stability as well as the efficiency. Now, it's not the only thing that we need to do. There's a lot more that we need to do to increase the stability further, and there's a number of companies working on this all around the world. But it's part of the steps forward in order to get a high stability as well as efficiency of perovskite solar cells. And you can see that the efficiency then is stable when you're keeping the light on and off for a number of days. So that was one way of increasing the efficiency of silicon solar cells. We've looked at a few other concepts as well. This one is using the same kind of ideas, but arranging the solar cells in a different way. So what we have here is the light coming in, hitting the perovskite solar cell over here, and then bouncing onto the silicon solar cell. So instead of having them stacked on top of each other, we actually have them stacked in a V-type configuration. So the advantage of this is that you can avoid some of the issues that you had with the transparency previously. So you can just have a metal contact on your back of your perovskite solar cell now. So we did this, and overall we were able to get an efficiency of 23% by using this kind of V-type configuration. Now, if you're going to have this sort of arrangement, you'd want to have pretty small cells, and you'd want to put them in a module, and you'd want that module to be tracking the sun. But they do have modules that track the sun already, so that bit would be straightforward. It would just be a matter of making the perovskite cells, again, so they're efficient and stable enough. And this is one of the most recent things we've tried. So we're actually using the perovskite and silicon solar cells in order to make hydrogen, because making electricity is not the only thing that needs to be solved, obviously, for sustainable energy into the future. We will also need some types of fuels. So we've started looking at making hydrogen using solar cells. So there's a few different concepts that you can think of in order to do this. You can arrange the solar cells in different ways, but basically the idea is you're using the solar cell to generate a voltage and generate a current, and you're using that to drive a chemical reaction inside the electrolyte, which will then split water to generate hydrogen. So this shows you our initial results so far. We have a perovskite solar cell here. We have a silicon solar cell here, and that's actually immersed in the electrolyte. And at the surface of here, we're generating bubbles of hydrogen and bubbles of oxygen. So what's happening here is that the light is coming in, hitting the perovskite solar cell, and hitting the silicon solar cell. And so we're getting the electrons transferred here, and that can drive that chemical reaction. It's not enough to drive the chemical reaction by itself. We also need the perovskite solar cell to provide some extra voltage, and that can make the chemical reaction favourable, and as a result you can split water. So by doing that, we've been able to get 16% efficiency going from solar to hydrogen, which is one of the highest efficiencies that's been achieved so far. So overall, I've said that we've seen a dramatic reduction in price of solar, seen dramatic growth. We've seen lots of interesting efficiency trends here, different types of solar cells for different applications. Silicon solar cells dominating the market, very high efficiency solar cells for space applications, and new types of solar cells that we can put together with silicon solar cells to increase the efficiency. Overall, we're expanding now in the types of solar cells that's being installed out in the field, and we're seeing very large systems installed now, as well as new materials that's creating new possibilities to increase the efficiency of solar cells further. And I think as a result, we can say that Alexander Edmund Becquerel would be pleased. Thank you.